Hello. In this video I want to discuss a simple example involving the, the tangent line to a curve given by a vector function. So we are given a vector function r of t. Its components are t e to the t squared plus 1, t squared minus t, cos t. And we want to find an equation for the tangent line to the curve given by this vector function r at the point p is equal to 1, 0, 1. Right. So recall that if p equals to r of a is a point on C, and the derivative of r exists at a, then we can write down an equation for the tangent line to the curve C at the point P as x is equal to r of a plus t r prime a, t an element of r. Right, and note of course that P is the point r at a. Okay, so what do we need? Well, firstly, we need to find the derivative of r. Right? So that we can do. Remember, we just differentiate component-wise. So the derivative of r at any point t is equal to e to the t squared plus 2t squared e to the t squared, 2t minus 1 minus sine t. Right, so we've got the derivative. Now, secondly, we must find r, a real number, such that r of a is equal to p. Right, now, so for a an element of r of a is a e to the a squared plus 1, a squared minus a, cos a, and this is equal to p, and p is, remember, the point 1, 0, 1, if and only if, well, remember, two vectors are equal when the corresponding components are equal. So we've got three equations. We've got a e to the a squared plus 1 is 1. We've got a squared minus a is 0. And we've got cos a is 1. Right? So we've got three equations. And we must find one real number that satisfies all three equations simultaneously. Now, looking at this, we see that, for instance, the second equation tells us that either a is 0 or a is 1. Now, these two values for a satisfy the second equation. But now we must check, do these also satisfy the other two equations? Well, if a is equal to 1, and we substitute it into the first equation, then we get 1 times e to the 1 plus 1, which is e plus 1. And that's definitely not equal to 1. On the other hand, if we substitute a equals 0, then we see that it does satisfy the first equation. Right. So from the second equation, we get a is 0 and a is 1. And the first equation tells us that a is equal to 1 cannot be a solution. Right. So now we need to check, does a equal 0, right? Our only remaining value satisfy the third equation. So if we look at 3, right, we know what cos 0 is. It's 1. So we can conclude that r of a is equal to p precisely when a is 0. So that means this is the value we have to look at. This is the point we get. So now, in order to write down the equation for the tangent line, we need to evaluate the derivative of r at a equals 0. Right, so we need to calculate derivative of r at 0. Right, so we substitute it back in here, our expression we found for the derivative of r. So e to the 0 is 1, and if we substitute t equals 0 to the second term, we're going to get 0. So it's 1 minus 1, 0. Okay. So now we can write down the equation for the tangent line. Right? It is r at 0 plus t derivative of r at 0. R at 0 is the 0.101 plus t, and we found the derivative 1 minus 1, 0, t an element of r. Okay, so that's a relatively simple example. Now, it's very important here that you check carefully your solutions when finding the point A so that r of A is P. Right? One reason why it's important, why you have to be very careful, is that it is possible for two different values of A to give you the same point. So for instance, the following is possible. And we can get, say, A of 1 is equal to, of R of 1 is equal to R of 2. And you've got different derivatives, and both are non-zero. Right, so what happens in this kind of situation? Well, in this kind of situation, the curve passes through the point P twice. Right, so we've got something like this. Right, so here goes the curve. It hits this point P when t is equal to 1. It loops back around like this, and it hits this point again when t is equal to 2. And now here we see that in fact we've got two tangent lines here. Right, we can draw two tangents to the curve. Right, one there and one there. Yeah. Right. So it's very important that we must check that we have all the possible solutions to the equation R of A is equal to P.